Okay, we're going to move on. Second part, mean and standard deviation of a binomial distribution. All right, so you roll a die, 2 die, 4 times. We're going to create a histogram, find the mean and standard deviation of the event. We're rolling doubles. The same number on each die is the same, is considered a success. So probability of rolling doubles is going to be 1 out of 6. So the number of doubles, probability of rolling said number, so 0, 1, 2, 3, 4. So I roll it 4 times, the probability that I roll no doubles, 1, 2, 3, and 4. All right, so let's go through, again, the binomial distribution here. I've done all the work and given the answers, but this is the work, and you can also do this, at least in part, in your calculator. So I have a combination of 4 with 0 successes. Probability of success is 1/6 the power of 0. 1 minus 1/6 the complement to the power of 4 brings me, 0.482. So I continue to do that for each of the number of successes. Combination of 4, choose 1. 1 is the success, 1/6 to the power of 1. Complement of that event to the power of 3. So I did that for all these. They should add up to 1. All right. So then I'm going to create a histogram here. And then from this histogram, I'm going to find the mean. It's 0.667. And then standard deviation is 0.746. All right, so you should be able to calculate all these on your own. All right, so the mean for binomial distribution is, again, the weighted outcome 0 successes times 0.42. Success 1 doubles 0.386, 2 doubles 0.116, 3 doubles 0.0015, 4 0.001. Total is equal to 0.667. All right. I can also take the number n times the probability. So n4 times 1/6 is going to be our formula. It's 4/6 that ends up being the same value. 4 times 1/6 is 0.667. So in rolling a pair of die 4 times, the mean number of times you roll 2 of the same kind is going to be less than 1, 0.667. And we can find that by taking n times p. All right, next we want to find the standard deviation. All right, so I have the variance is equal to, as before, the value minus the probability. So minus the mean. So the value minus the mean times the probability of that outcome plus the value, weighted value, or the x value 1 success minus the mean squared times the probability of that outcome plus outcome 2 doubles minus the mean squared times the probability of that outcome, and so on and so forth until you get 0.556. And then you take the square root of that value, and that ends up being 0.746. Now, if we were to work this out mathematically, it's the same as the square root of n times p times 1 minus p, the complement of p. So n times square root of n times the probability of the outcome 1/6 times the complement 5/6 is equal to 0.556. So same value here. Square root of this is standard deviation is 0.746. All right, so these two formulas is very important. Mean NP is equal to number of outcomes times the probability, and then standard deviation is the square root of the number of outcomes times the probability of that outcome times the complement of that outcome. All right, so here's an example. What happens if the probability is not 0.5? And we're going to work with N and P again and our formula. So about 33% of students own an electric book reading device. They ask 4 randomly chosen students. If they have a book reader, what is the probability that you have 0, 1, 2, 3, 4 students own a book reader? All right, so define NP and K. So I've done here below 4 students chosen. Probability is 0.33. Number of successes between 0 and 4. All right, so I've done all my calculations here. Now I want to calculate the mean and standard deviation. So remember I summed here, it's very close to 1. Right, so mean is n times p, 4 times 0.33 or 1.32. And then the standard deviation is the square root of np times the complement of p, 4 times 0.33 times 0.67. Take the square root of that value is equal to 0.94. So I have a mean of 1.32 and a standard deviation of 0.94. All right, and I can do this using binomial CDF. When I ask what is the probability that 3 or more say they own an e-reader. Right, so the probability, now I'm using the mean and standard deviation to find out some probabilities, and I want to find out the probability that 3 or more say they own an e-reader. It's the same, so remember we're measuring to the left of whatever the value is, so we want to say what's 1 minus the probability of x is less than or equal to 2. So 4 times the probability of success times the number of successes. In a binomial CDF, 1 minus that value is 0.10817. And then we can go to the hand calculations below and take the probability of a 3 over 4, add them together, and we get basically the same number. All right. Sure. So this is a lot of information for you. You can pause here to look through how this is calculated. Right. So first, we found the outcomes here. Then we did this, calculated the mean and standard deviation outside of these outcomes here using NP. We used the mean and standard deviation to calculate the number of successes using a calculator, knowing that the calculator is going to provide us with the area to the left. We were looking for the area to the right in a standard normal curve. All right, so then what is the probability that exactly 2 people say they have an e-reader? So same thing, we're going to use binomial PDF. We get 0.2933, that checks out. So we're checking our work against the calculator. I strongly suggest you do the same. So this brings us to homework 6.3.2. Flip a coin 4 times. What's the probability that you flip all these, and then, which you've already done? What is the mean number of times you flip tails from 4 flips? What's the standard deviation? And what's the probability that you flip 3 or more? All right, so we're going to take that information that you've already developed and then find the probability that you flip 3 or more. All right, so moving on, binomial distributions in a statistical sampling. A drawer has 8 AAA batteries, so I'm going to give you an example, but only 6 of them are good. You need to choose 4 for graphing calculator. What is the probability that if you select 4 from the drawer, all 4 will work? So you're selecting without replacement, so the selection is not independent. However, sometimes lack of independence is not an issue, so we need to consider that because sometimes we don't have complete dependence. So the real answer is 0.2413, so you have to be careful. The bad answer, the binomial distribution answer, is 0.3164. All right, so binomial distribution when considering sampling without replacement. So we have to be careful if the events are not independent. When we sample without replacement, we're creating a situation where the sampling is going to be create some dependencies because we're removing the base denominator value, and so we're increasing the probability that the next person chosen will be some person. However, you can use binomial distribution in the case where we have dependence, but the sample size is less than or equal to 1/10 of the size of the population. And it's okay to use binomial distribution. All right, so what's happening is where n is equal to 10, the probability is 0.8. N is equal to 20, 0.8. N is equal to 50, probability is 0.8. You can see how the curve gets tighter and tighter around a particular location. So as n gets bigger, the distribution represents a more normal curve. Right. So normal approximation for a binomial distribution. Suppose a count x as a binomial distribution with n trials and successes, probably p. When n is large, the distribution x is approximately normal. Right, so going back to our example here, as the number of trials gets bigger and bigger, then the curve represents a more normal distribution. So in order to test for normal distribution, right, we need to figure out what n is going to be. So we're going to use n, of course, for the mean and standard deviation. So the rule of thumb now we're going to use is that we can use normal approximations when n is so large that the expected number of successes and failures are both at least 10. So when np is greater than 10, and when n times 1 minus p is greater than 10, then we're okay using the standard normal distribution. But when they're not both, then we have to be careful. All right, so here we go with calculating probabilities. We have some requirements. We need to show that the distribution of x is approximately binomial. If it's not, so binary independent number of successes and the probability of success are all given. If it's not independent, then we need to show that the sample size is less than 1/10 of the population. Then we can move forward. Secondly, we need to check to see if the distribution is normal approximation, and we can assume normal approximation if n times p is greater than 10 and n times the complement is also greater than or equal to 10. So the number of successes and the number of failures need to be greater than or equal to 10 each. Then we can use a normal CDF to find the mean here and the standard deviation given these values. But these two criteria need to be met, actually three. So the bins, and if there's the dependence, then sample size is less than 1/10 of the population. And then to use a normal approximation curve, which is separate from A, then both NP and so the number of successes and the number of failures each have to be greater than or equal to 10. All right, so we're going to pause here. Okay, so now let's qualify what we're doing here in the context of a question. Because really what we're doing is not only are we using some of the formulas, but we're also trying to categorize some experiment or distribution in a way that we can assess with our given paradigms for normal distribution and qualifications for the bins feature for a normal binomial distribution. All right. So in a survey, so hopefully these examples will help you. So in a survey of 2,500 adults, they were surveyed whether they enjoyed shopping. It's known that 60% of the population does not like to shop. So show that the distribution of x is approximately binomial, binary independent number of successes. Now, if it's not independent, then you have to show that the sample size is less than or equal to 1/10 of the population. But if it is independent, you don't have to worry about it. Then check the conditions for using normal approximations for the setting. So remember, NP and n times 1 minus p have to be greater than or equal to 10. And then use a normal distribution to estimate the probability that 1,520 or more of the sample do not like to shop. So then we can move on to our probability tables. All right, so it looks like yes, binary, it's like or don't like. Independent, no, but n is less than 1/10 of, or equal to 1/10 of the entire population, right? Because we know 2,500 adults is less than the entire population of adults in the United States. Now we're going to check the conditions for using normal approximation. NP is greater than 10, and n times 1 minus p is greater than 10. So we can assume a normal approximation for the setting. Now we're going to use our normal distribution to estimate the probability that 1,520 or more of the sample do not like to shop. All right, so I'm going to find out what the mean value is, 2,500, n times p, 2,500 people times 0.6. And the standard deviation is n times p times 1 minus p, and then the square root of that value. is 24.49. And then I want to find the probability that x is greater than or equal to 1520. Using our z-scores, we can find out the probability of z is greater than or equal to 8.816. What's less than 0.816 is going to be, for a z-score of 0.816, and if you look at the table, it's 0.794. So the probability that it's greater than 0.816 is 0.206. So there's a 20.6% chance that 1,520 or more will answer that they don't like to shop. So remember, in this calculation, when we get values for the standard normal curve, it's going to be less than the area, less than a given z-score. And because we want what's greater than, we have to use the complement of the event. The complement of what's less than is 1 minus what's less than. All right, and we end up with 20.6. All right, so moving on. This brings us to your homework. So I'm going to pause here, and I think I'm going to end potentially, because we're going to move on to binomial or geometric distribution. It's going to be a separate video. So take this down and then come back.